Welcome everybody to my lecture. It is my great honor and pleasure to present at this conference. I'm really thankful to the conference organizers. The title of my presentation is Modern Predictive Control, a Rising Technology in the Automotive Industry. This is the outline of my lecture. I will first describe in a few words what modern predictive control is, and then I will show you some concrete examples of application of MPC in the automotive industry. I'll then talk about embedded quadratic optimization for MPC, and then about ideas for help the calibration of MPC controllers. And finally, I will discuss ideas on how to combine some tools from machine learning with MPC. So what is modern predictive control? It is a control technique, so we have a feedback loop. The particular feature of MPC is to use in the controller a model of the process that we are controlling to make predictions of what the process will do if a certain sequence of manipulated variables is applied. And among all these possible sequences of manipulated variables that you can choose, the MPC controller will choose the best one according to a certain performance index and constraints that I will specify in a second. This is why it's called modern predictive control. Use a model of the process to make predictions, and as a result of the optimization, you get a control action. So the optimization problem is usually based on a quadratic performance index where you penalize deviations of the predicted output from the reference signal, so the tracking error, and also you have penalties on the inputs. This could be, for example, the penalties on the deviation between the inputs that you want to apply and the corresponding steady-state optimal inputs. Or could be penalties on input variations to smooth out the control action. So this is a finite optimal control problem that you set up for the current time t by looking ahead n steps in the future. So the optimal control problem is over n future steps. It is based on a prediction model, so the states evolve in the prediction according to a model that you need to choose. And you can also include constraints. This is actually why MPC is very useful in practice. So you can include constraints on inputs and output variables in the optimal control problem formulation. Note that the optimal control solution depends on the initial state for the optimal control problem, that is the current state x of t that we measure or estimate at time t. So the optimal control problem can be mapped into a numerical optimization problem. And the idea of MPC is the following. So we estimate the current state first, then we optimize with respect to the sequence of inputs the optimal control problem we solve, and then we apply only the first sample of the sequence. Why we want to apply only the first one and throw away the rest of the optimal samples? Because at the next time step, we will acquire the new state, xt plus 1, and possibly revise your optimal decision. So we will solve again an optimal control problem between time t plus 1 and t plus n plus 1, and so on. So as a result of this repeated optimization over time, we get that the control action that we apply is always a function of the current state and the reference signals and other signals that we inject in the problem formulation. If the prediction model is linear, then the numerical optimization problem can be mapped into a quadratic programming problem. Now, the idea of MPC is not new. Actually, one of the first papers describing receding horizon control ideas, like the one I just presented, dates back to the late 60s. There is a paper by Rafal and Stevens. One of the authors was affiliated with the Esso oil company. It's called Discrete Dynamic Optimization Applied to Online Optimal Control, where you find this idea of repeatedly solving an optimal control problem online. There is even a paper in the Russian literature appeared in the early 60s where linear programming was proposed in a receding horizon fashion, again, to synthesize a digital control law. Now, since the time, starting around the 80s, MPC has been steadily applied in the process industries as an advanced process control technology. And today, most of the APC solutions are model predictive control solutions in the process industries. Now, how about the automotive industry? Most, if not all, automotive OEMs these days are looking into MPC solutions today. It's not only me and my research group and the companies I'm collaborating with, but there are several research centers, universities, and companies, automotive companies, that are these days looking at model predictive control technologies for the next generation of automotive controllers. Let me mention one of these applications that we have been doing with General Motors and my company Otis in the past years. So we have been looking at engine control. So for a gasoline turbocharged engine, you want to design a controller that is able in real time to generate signals for the throttle, wastegate valves, and the intake and exhaust cams. The task is to achieve a certain engine torque while maximizing efficiency and satisfying a series of constraints that you have in the problem. Now, how did we address and solve this problem? Well, the engine is quite nonlinear, so we derived many linear prediction models in order to cover the different areas of the operating range of the engine. Actually, we scheduled the models according to a grid in a three-dimensional space. One of the coordinates is the engine RPM. And in each of these zones, a linear prediction model was identified using black box system identification. And then for each model, we have a corresponding linear MPC controller and an associated state observer, which is a Kalman filter. Now, the number of models that you choose and how you schedule this model is quite important for closed-loop performance. It is also important what you specify as reference signals for the inputs. So in this case, in the cost function, we included a term penalizing the difference between the predicted input that we optimize and the steady state value of the input, which is optimal for the current reference signal for the output. Now, note that this is a multivariable control problem where you have one output and four inputs. So in principle, you have many combinations of inputs that give you the same steady state value for the output. And that's why for fuel efficiency, you need to specify the right set point values for the inputs. The controller structure is a set of linear MPC controllers and the corresponding Kalman filters. The main tuning parameters of the controller are the weight on the output tracking error and the weights on the inputs and their variations, and also how much you penalize the violation of output constraints. Output constraints are treated as soft constraints in order to make sure that the quadratic programming problem that you need to solve at each time step is always feasible. This is a different application that we have been looking at together with General Motors and Otis. So the problem here is to make the vehicle deliver a certain axle torque. So it's a higher level of control where what you command is the set point, torque set point to the engine. And also this is a CVT, continuously variable transmission configuration. So what you also command is the ratio you want to have at each sample step at the CVT. And the two controllers were put in production by General Motors starting in the fall of 2018. GM started a mass production of vehicles embedding the MPC controllers that I was mentioning before on board of the vehicle. And as far as we know, this is the first and least documented mass production of MPC in the automotive industry. And I consider this quite an achievement because we could prove that MPC is not just a technique for process control, but is also a viable technology for the automotive industry as well. Now the question is, do we really need advanced control? So could we do the same with, say, more classical control methodologies? Well, we have to consider that the requirements in terms of emission and consumptions, and also passenger safety and comfort and others, are increasingly demanding. And also the control problems start getting more and more complicated. For example, if you consider electrification on the powertrain, then the number of actuators starts increasing. So you have valves and other signals, as well as electrical motors, and they all contribute to deliver a torque. Also, the actuators that you use, they have always limited range. You would like to use the maximum available power that you can get from the actuators. And also you need resilience in case of actuator failure. So if one of the actuators fails, you will still like the controller to behave at best as it can, given the remaining actuators. There is also another aspect to take into account, that the time to develop a new controller is getting shorter and shorter. The timeline for control development is shrinking, and this is due to different aspects, for example, market competition or changes in the legislation. So the requirements change, you have to revise and change your control design. So with classical control, you can achieve good results, and typically classical control is done with several PID loops with anti-windup to take into account actuator constraints, and also different lookup tables to compensate for the dynamic coupling between different loops and to optimize performance. So you can achieve good performance in closed loop with the classical control, but the drawbacks of this approach would be the complexity of the design. If you think about having several actuators to coordinate, then the number of interactions is high, and you have to deal with all these type of interactions. And also, if you have to take into account actuator failures, you have to have a strategy, a backup strategy for each possible fault that you can envision. And talking about lookup tables, say you have 5 inputs and you say allow 10 different values in the table for each of the inputs. This is already 10 to the power 5 entries that you have to fill in the lookup table. So that makes the coordination of multiple actuators and their constraints difficult, and especially if you want to optimize the overall behavior. And there is another aspect. Even if you are able to achieve very good performance with more classical control techniques, then if the engine changes, you will have to revise the design, and then it may take a long time to redefine the new lookup tables or the new configuration to take into account these changes. So that's why automotive companies are looking in more modern control techniques that can, on one hand, achieve the same level of closed-loop performance or even better, and also shorten the development time of the controller. And MPC is one of these techniques. Now, what are the key challenges for developing an MPC controller that can be put in production? Well, I'm listing here what I consider the 3 main challenges. One is online optimization. You want to solve the optimization problem associated with the MPC in real time, so you need to have a very fast and reliable optimization solver. And the question is whether we can avoid this. I will discuss about this in a second. And then the second challenge is modeling. Usually the most time to develop an MPC controller is taken by getting the right prediction models to use in MPC. And the question is whether we can shorten this model development time, for example, using data and black box identification tools. And also calibration. So we can come up with a design rather quickly, maybe in simulation, but then when it comes to the real engine or to the vehicle, we need to calibrate the controller. And this also can be a time-consuming task. So if we have tools to shorten calibration time, that's also good to push MPC for production. So I will discuss about embedded quadratic optimization. So As I mentioned, in case of linear prediction models, the optimization problem you need to solve at each time step is a quadratic programming problem. So it's a problem of minimizing a convex quadratic function subject to linear inequalities that collect all the constraints you have on inputs and outputs. And you want to solve this problem with respect to the sequence of inputs over the prediction horizon. Now, this is also not a new type of problem that you want to solve. The literature on quadratic programming dates back to the 50s. You find papers in the operations, research, and management science literature since many, many years ago. And as a result, these days you have a large set of different solution methods that you can use to solve quadratic programming problems. Now, not all of these methods are good for industrial embedded control. Why? Because if you want to embed an optimization solver in a platform, you need to satisfy certain number of requirements. I'm listing here what I consider the main ones of such requirements. Of course, speed. So you want the solver to be fast, not only on average, but especially in the worst case. You have real-time, hard real-time constraints, and you want to make sure that your solver delivers the solution within the allocated time. Also, memory is still an issue. If you look at current control platform, typically you have available CPUs that can run 150 megahertz, and you only have, say, a few tens of kilobytes available for your controller. Why this? Because MPC is not the only control task that is running. You have several other functions running on board of the vehicle, so they have to share memory and the resources. So your solver should be able to run with a limited CPU and without consuming an excessive amount of memory. It must be very robust numerically. Still, a lot of applications run in single precision arithmetic, so your solver should be robust enough to tolerate such low precision. And also you would like to be able to certify the worst case execution time, so for the reason I was mentioning before. And regarding the code, the software code that implements the solver, this should not be too complicated. Actually, it should be simple enough. It should be library free, because then you want to certify the code, so you want to actually analyze and certify the code. So you also have to make sure that there are not interactions with libraries that are not foreseen in advance, so you want to inspect the whole code, and this should be easily inspectable by software engineers in production. And even in some applications, you want to run formal verification methods to make sure that the software always runs correctly in the platform. Let me give you an example of why solving the QP problem accurately is important. This is actually an example motivated by a real application. So let's say you have a multivariable MPC controller that runs at 40 Hertz, which means that you are solving one QP problem every 25 milliseconds. And say this is running on a vehicle that operates 1 hour a day over 360 days on average, and that this controller is running on 10 million vehicles. Now, if you do some simple math, you end up solving about 500 quadrillion QP problems every year, and no one of them should fail. So that puts some pressure on us developing the optimization solvers for MPC. You have to make sure that the software implementing the QP solver and the algorithm is very, very robust. Different methods have been proposed in recent years in the literature to solve quadratic optimization problems in an embedded environment motivated by MPC applications. One of them is the regularized version of the alternating direction method of multipliers. Actually, the algorithm is summarized in these 3 lines here. So you have to compute the factorization of these metrics beforehand. if you are solving a linear time invariant MPC problem, or online if the problem matrices change. And then once you have factorized the matrix here, you iterate these iterations listed here. So the code is really simple. It's quite fast and also quite robust numerically. And this is implemented in the OSQP solver. You can download from here. And it has been downloaded several times. The Python interface has been downloaded more than 1.7 million times. And we have extended this also to solve mixed integer quadratic programming problems for solving hybrid MPC in an embedded platform. This is another method I investigated recently. So the idea is to take the convex quadratic programming problem, assuming it's strictly convex, and complete the squares by doing a change of coordinates, and then remap the problem into a least distance problem. Now, it is well known that this least distance problem, can be solved by a non-negative least squares solver, which also has a very simple algorithm based on an active set method that you can use. It's described in this book by Lawson and Hanson. And it's based on solving a least squares problem with non-negativity constraints on these variables. Now, if the problem when the problem is solved, the residual can be 0. In this case, you can prove the QP, the original QP was infeasible, and this should never happen in an MPC application. Or otherwise, if the residual is non-zero, then you can retrieve the solution from the optimal solution of the non-negative least squares problem. Now, this is not a very robust approach, so lately I've been investigating a method that does proximal point iterations around this non-negative least squares solver, and as a result the method becomes quite robust. And here are some plots showing how the methods behave when implemented in single precision arithmetic on a type of problems that you would encounter in typical MPC applications in automotive problems, like you have 30 variables and 100 constraints. So the solver is fast and also is numerically quite robust compared to a DMM or to accelerated gradient projection. And these also be extended to solve mixed integer quadratic programming problems. Can we do MPC without online optimization? In some cases, you don't want to use online optimization. Why? Well, it could be very fast sampling one, so you don't have enough time to solve the problem, or you cannot embed the software, so people will not be willing to implement the solver on board of the platform. Well, in this case, the answer is yes. If the model is linear, time invariant, and the constraints are linear, and you have a quadratic objective, you can pre-solve the optimization problem offline by solving a so-called multiparametric quadratic programming problem. So in multiparametric programming, the idea is to look at the quadratic programming problem, where if the model is LTI and the cost function doesn't change, the matrices Q and G are constant, and as well as these other matrices here. What only changes at runtime is the value of the state vector and possibly also the reference signal and other signals, for example, the upper lower bounds of the constraints, that you can summarize in a vector X of parameters. Now, these type of problems can be solved explicitly. This is described in this paper. And the solution is piecewise affine and is also continuous. That means that the MPC control law that you apply, which is, remember, is the first component of the QP solution, is a continuous piecewise affine function. So the MPC controller is nothing else than a lookup table of linear affine gains, each one defined in a polyhedral cell. And the polyhedral partition is automatically generated by the multiparametric solver. So actually, even if you don't implement the controller using multiparametric programming, so as an explicit function, even if you solve the QP problem online, you know that what you are applying is a continuous piecewise affine control law. And this is now implemented in the MPC toolbox starting in the release 2014B. And the algorithm implemented in the toolbox is based on a multiparametric quadratic programming solver using non-negative least squares to do the computational geometry that is described in this paper. So the question is whether implicit MPC is worse or better than explicit MPC. This is a question that usually you don't know exactly how to solve. You can analyze the complexity, especially the worst case complexity of an explicit controller. Is less obvious what is the worst case complexity for the online optimization. In this paper with Jonathan Cimini, we could prove that if you take an active set, dual active set method for QP, the number of iterations that the QP solver makes is piecewise constant with respect to the vector of parameters. So offline you can run an algorithm similar to the multiparametric programming solver that will cover the entire space of parameters, and after the algorithm stops, you can actually throw away the whole partitions that you got and just record a number, in this case 5. You could prove that, at least in this example, the active set solver never makes more than 5 iterations, never ever, okay, because you have covered the entire parameter space. So that's allow you to certify how many flops the QP solver will make in the worst case. And there have been other papers by Daniel Axelhill and the collaborators showing how the method works also for different type of active set methods. And now you can compare MPC done using online optimization with MPC done using an explicit version of the controller. And here you see 4 simple examples taken from the MPC toolbox. For example, here you see that explicit MPC is faster in terms of flops in the worst case compared to online quadratic programming, although it takes more memory to store the partition that the memory taken by the solvers and the QP matrices you need to store. While in this other example, you see that explicit MPC takes 16,000 flops in the worst case, while the active set method using this algorithm, you can prove that it never takes more than about 8,000 flops. It also takes less memory. So you have a way of analyzing offline precisely without any approximation, really precisely, what is the number of flops you will encounter if you either implement an explicit version of the controller or if you solve the QP problem online. Now, regarding calibration of MPC controllers. The MPC controller depends on several parameters. Let's call X these parameters that are the tuning knobs of the controller that we leave free to choose to the calibrator. This can be the weights you use in the MPC cost function, or the prediction and control horizon, or even the coefficients of the prediction model. This can be treated as tuning knobs. The covariance matrices you use in the Kalman filter, and even the tolerances that you use in the solver, these can all be treated as calibration parameters. Now, how to automatize the calibration process? Well, you can define a performance index, a closed loop function that quantifies how good is your closed loop performance. For example, you can look at the sum of square tracking errors over a certain simulation horizon or over a duration of an experiment. Okay, and then try to minimize this function with respect to the tuning knobs. Now, this is a global optimization problem that you want to solve. So you want to minimize a rather complex function that depends on closed loop, on the closed loop behavior of the system with respect to the tuning parameters. How to solve this problem effectively? So I'm listing here a few methods that are good for this type of global optimization problem you encounter in Autotuning. These are well described in this survey paper by Rios and Ioannidis. And I recently developed a new method called GLIS for radial basis functions and inverse distance weighting, meaning that this is a method that belongs to the response surface methods. The idea is to fit a function to your function samples that you get at every run of an experiment or of a simulation, and then use this surrogate function to drive the search for a new set of calibration parameters to test. Let me show you some examples of how this works. Say you have a simple tuning problem of an MPC controller, one input, one output. You want to choose a value of the weight on the input increments. Okay, so to trade off between tracking errors and the smoothness of the control action. And also you leave the control horizon as a degree of freedom. Ideally, you would like to minimize the number of degrees of freedom you have in the optimization, because this is a proxy for the complexity of the quadratic programming problem. So let's take the logarithm of the weight and the control horizon as our calibration parameters. Say we assign a range for these values, and as a performance index, let's look at the sum of tracking errors and also at the square input increments as well as the control horizon. Okay, so we want to minimize this function. So if you run the solver, you will end up with a controller that has this weight on the input increments and the control horizon of 2, and this will be the corresponding closed loop response. And this is how the closed loop performance evolves over the iterations. Okay, so it settles on a small value after about I would say 70-80 tests. You will get a very good value for the tuning knobs, actually even before you get already decent values. Let me show you another example which is described in this paper with Michael Fuegione and Daniel Piga that was presented recently at the IFAC World Congress. So here again is a simple MPC problem. You want to control the position of a pendulum on a cart. Here your closed loop performance you want to look at is how much you deviate from the reference position, and also what is the deviation, the angle of the pendulum over the simulation or the experiment horizon. Various MPC tuning parameters were tuned here. We have 14 of those parameters: the sampling time, the weights on the outputs and input increments, the prediction and control horizon, the covariance matrices of the Kalman filter, as well as the absolute and relative tolerance in the QP solver. So this was solved using the GLIS global optimizer by running 500 iterations. And this was tested on 2 different platforms, on a PC and on a Raspberry Pi. That are actually used, the actual hardware is used during the evaluation of the cost function to really have right measures of how the solver behaves on the platform. And you can see here the results of the auto-tuning procedure. Actually get 2 different tunings. For desktop PC, you get this optimal sampling time of 6 milliseconds, while you get 22 milliseconds for the Raspberry Pi. And this is an overall trade-off between all these calibration parameters. So you can say that this type of auto-tuning procedure squeezes out the maximum performance that you can get given the control platform that you have available and the MPC controller structure that you have chosen. Pros and cons of this type of auto-tuning approach. Pros are that the calibration process is completely automatic and is applicable to any of the calibration parameters. And the performance index is rather arbitrary, so you can combine different things, not only tracking performance, but also response time, overshoots, worst case number of flops, so all kind of things that you can numerically quantify. This can be taken into account in the performance index. Now, the cons of this approach is that you actually have to quantify an objective function, and often this is not easy to do. Often you have multiple objectives that you want to take into account, and you don't know exactly how to blend them. So you will actually like to see the results that you get, and then maybe judge whether some of the objective is met correctly or should better met by the controller. And also, this approach doesn't leave any room for qualitative assessments. So the result is purely driven by the numbers you get out of the cost function. It doesn't leave the judgment of the calibrator in the loop while optimizing. That's why recently we developed a new approach which is based on preference. It's actually a preference-based version of the algorithm I just described before, and it's still included in this package that I put online. It's both based on a MATLAB implementation and alternatively on a Python implementation of these two solvers. And this can be used for semi-automatic tuning. This is actually ongoing work together with my PhD student Mengja Zhu and Daniel Piga. So what is the idea here? The idea is that you assume there is a function, there is a performance index that you are optimizing, but you don't know what it is. So this guy lives in the inside the calibrator is an unconscious score function that the calibrator has in order to judge the outcome of a certain experiment or simulation. Now, the idea of active preference learning is to have an algorithm to construct a surrogate of the latent function and use this function to propose a new set of parameters to test. Then the calibrator is only asked to give a preference. So whether in particular the new setting of parameters is better or worse or the same as the current best one that has been obtained so far. Here is the same example I was showing before, now run with the preference based optimization. You actually get very similar results, and now there is no knowledge about the closed loop performance index. Okay, it's only based on comparison on whether a certain guess is better or worse or equivalent to another one. So this brings me to the last part of my presentation. I want to discuss what are possible future trends in advanced control in the automotive industry, and not only the automotive industry. If we consider how controls have evolved during the years, starting from pure mechanical design, controls have been having changes in design paradigms and additional design techniques added to the set of techniques that is available, often due to advances in other domains. So now the question is, what would be the next step in this historical path? Well, probably machine learning will be influential in the way we design control systems. Actually, you can witness this already in R&D centers in industry. A lot of attention is devoted to MPC and to machine learning. What is machine learning? Well, in a nutshell, it's a set of techniques to extract mathematical models from data. And these models can be used for classification, for prediction, or for decision making. It has very good mathematical foundations from artificial intelligence, statistics, and optimization. And very important, it works really well in practice, in spite of the fact that the training of the models is often based on very non-convex optimization problems that still you are able to solve. Now, what can machine learning do for MPC? Well, it can help in many respects. I want to focus on the first, so how we can use machine learning to get prediction models from data. And the approach is quite intuitive. So here, instead of using a physics-based model or a black box model obtained by fitting linear prediction model, different linear prediction models to data, we want to use a neural network to make predictions over an horizon. If we use a neural network, it will be a nonlinear system, so we have to deal with a nonlinear MPC formulation. One approach to solving this problem is to build on top of the existing tools that have been developed for linear time-varying MPC, in particular quadratic programming, so how to construct the QP problem and how to solve the QP problem robustly online. So we can build on top of that by solving a certain number of QPs at each sampling step. So let's say we have the current state and the initial guess for the optimal input sequence. That could be, for example, the previous optimal sequence shifted by one sample, that we can take it as an initial guess. We can simulate the model, so to get the predicted nominal state trajectory, and then linearize the system around this trajectory. So in this case, it would be the neural network to be linearized with respect to the states and the input signals. And then we can, after we linearize, we can construct a quadratic programming problem and solve it in order to get a new optimal sequence. And we can iterate this by refining further and further the optimal control sequence until we converge to a solution of the nonlinear MPC problem. You can actually prove that this is a sequential quadratic programming approach that you use to solve the full nonlinear MPC problem. You're not guaranteed to converge to a global minimum in case you have several minima, but it certainly will converge to at least to a local minimum. And actually, in practice, you often see that just one QP is enough for having quite good performance, closed-loop performance, which is nothing else applying a linear time-varying MPC configuration, which is also known as a real-time iteration scheme developed by Moritz Diels and others. This type of approach is taken in this commercial software toolset developed by Otis. It supports linear and nonlinear MPC control and extended Kalman filtering, and it's quite flexible, so you can change at runtime virtually everything, the models, the prediction horizon, the weights, the constraints, everything in principle can be changed at runtime, because the QP problems are constructed at runtime using a very, very efficient C implementation of the constructor, as well as the QP solver that has been implemented, and it's library free and MISRA C 2012 compliant, so that it can be used in automotive applications, and is actually currently used worldwide by different automotive OEMs in R&D and production projects. Let me show you an example of how to use neural networks to solve nonlinear MPC problems. Here I'm taking a simple problem of controlling the oxidation of ethylene process to ethylene oxide. The physical model is, you can write it down, it's quite nonlinear, and we don't want to use this model for predictions. So what we have done is to consider an MPC controller based on a switched linear prediction model and on a neural model, and compare it to a nonlinear MPC controller based on the exact physics-based model. So let's say you have designed a nonlinear MPC with this type of sample time, prediction horizon, etc. And for the neural network, we have trained a network which is quite simple. The model has 6 inputs, which are the 4 states, and 2 inputs and 4 outputs, which are the states at the following time step. Already with 1,000 samples and 2 hidden layers of 6 neurons, you get quite a good fit. So you see here the results on some validation, data not used for training. You have pretty good fit. And we train the neural networks and get automatically also the Jacobians with respect to the states of the inputs that are used then in the QP construction routine to build the QP problem. So you see here the results. With switch a linear MPC, you still can track set point changes in spite of the nonlinearity, but you see some overshoots, and these are mainly due to the fact that during transients you have quite large modeling errors. With the same model, so in nominal situations tracking, you get this type of tracking with this control configuration we have chosen. And if you use a neural network model, then you get quite similar closed-loop performance. And this is achieved without any knowledge of the physical model. So just by using these 1,000 samples generated offline to fit a model and use directly that as an MPC prediction model. So what can we say about the use of neural networks for MPC? This has been investigated since a few years. I think they can speed up the MPC design process quite a lot. Again, developing the models can be very time consuming. The good thing about using neural networks, contrarily to linear system identification, is that you don't have to predefine operating ranges and design different experiments for to cover different operation domains, but rather it's a one-shot modeling step. So you can collect data for the entire operating range and then fit one model to the entire data set. How about physics-based model? I think you shouldn't throw them out. Experience tells that those physics-based models are usually better to predict unseen situations because you are injecting knowledge of the physics in the model that you don't inject in a black box neural network models or other type of black box models. The calibration of the model parameters can be simpler because you have typically less coefficients to calibrate, although you still will have to run experiments and design your experiment properly to calibrate the parameters of the physics-based model. In some situations, however, getting the physics-based model that is good for MPC is not simple. Either because the underlying physics is too complex, you don't know how to model it, or because even if you don't know how to model it, the resulting model can be too complicated to be used in MPC and also to calibrate. Still, physics can be useful, for example, to decide the model structure. Maybe you don't design just one general black box neural network, but you can give a structure to the model. For example, use a mix of physics and model with neural networks the part that you don't want to model with physics, or you can use combinations of linear models and nonlinear neural models to get a prediction model. So you have all kind of configurations you can use, and often physics help deciding the right structure. So to conclude my presentation, we have witnessed a long history of success of MPC in the process industries for a long time. The reason for this success was that MPC was able to deal with large multivariable processes with constraints, and it's actually quite intuitive to design and to calibrate. I've seen teams of calibrators with initially no experience on MPC that found calibrating this new type of controllers quite relatively easy because it's intuitive. The effect of the weights, so you know that if you increase a weight on input increments, the control action will be smoother, or if you increase a weight on a certain output, the tracking should be better for that output. And constraints are obvious, and it's not only easy to calibrate but also to reconfigure. Okay, so in the process industry this was successful, so why this is now possible in the automotive industry too? Many reasons. I'm listing here what I consider the main ones. First of all, modern ECUs still are not very powerful, but powerful enough to solve MPC problems in real time. Also, the availability of good software tools that can assist you in the design and also in the deployment of the right software in the control board is an enabler for this technology and is required to be successful in deploying this technology. There is the push from the market to develop high-performance controllers in a short amount of time. So that makes MPC one of the technologies that can achieve that. And also, last but not least, production managers are now willing to deploy MPC controllers in the vehicle. And with an eye towards the future, I think that MPC based on deep neural models has high potentials. We'll see in the next years. And this concludes my lecture. I thank you very much for your attention.